Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I am going to continue with your same module, that is the database design concepts, but with the new chapter, that is chapter number 12, that is the query processing. In the last chapter we have finished with the chapter number 11, that is the indexing and the hashing. So today I am going to start with the new topic, new chapter, that is chapter number 12, that is the query processing. As the name advises, query processing means how to process the query, or what is the criteria to process the query, that is a query processing. That is a query that is written in the SQL, that is how to process, or what is the procedure to process the query, that is a query processing. So query processing refers to the range of activities that is given or that is involved in extraction of our records in the database, or extraction of the records or data from a database. So whenever we extract any record, whenever we extract any data from the database, that is known as the query processing. So it involves a range of activities, that is multiple activities are involved in extracting the data from a database. The activities include translation of a queries in a high-level database languages into expressions that can be used as the physical level of the file system. So these are the activities that is included in this one, that is the translation of the queries in a high-level database, in a high-level database languages into expressions that can be used at the physical level of the file system. That means translation of the queries into the high-level database languages that converts the database language into various expressions that can be used at the physical level of the file system, a variety of query optimization, transformation, and actual evaluation of the queries. So query processing means what are the various activities that is involved in extracting the data from a database, that is how to get the data from the database, that is the query processing. Now, what is the overview? That is the overview of the query processing that is required in how to process the query. So suppose I have given the query, any query, that is select the name ID from the table employee, from the relation employee. So how to process the query? That contains various range of activities, that contains various activities that is involved in extracting the data from a database. That involves, or that includes, a translation of a query into expressions at the physical level, a variety of query optimizing, transformation, and the actual evaluation of the query. That is, first of all, translate the query into high level database, then forming the transformation into the physical level, then making the transformations and actual evaluation of the queries. That is how to evaluate the queries and how to make the output from the queries. Now first is the overview. The steps involved in processing a query appeared in the figure 12.1. This is the 12.1 figure. So first of all, there is a query that is given by the user. There is a parser and the translator. This is the technique that is used, that is represented in the diamond. So parser means to convert the query into the various expressions. Translator also means convert the query into various, or change the query into various expressions, that is a relational algebra expression. Then there is an optimizer that is also related with the stats or statistics about the data. Then there is execution plan, that is how to execute the data. The plan will be carried out for executing the data. Then there is a evaluation engine, that is the evaluation engine means a kind of the motor, a kind of the rotation that will be formed for evaluating the result, that is the evaluation engine. Then there is a query output, that is the output of the query that can be formed, that is a query output. Then from the database there is the data that is required, that is done for using the data. So these are the various steps in the query processing. So first of all, the query come, then there is a parcel and the translator, then there is a relational algebra expression, then there is a optimizer, then there is a execution plan, evaluation engine, and the query output. And from the evaluation engine there will be a data, and the optimizer contains the statistics about the data. So this is the figure. Now let's see about the theory, that is what are the various steps. So steps are the parsing and the translation. This is the parsing and the translation. Then evaluation engine, then optimizer. So this is the optimizer, optimization, and then evaluation. So these are the three main steps that is required, or that is needed while processing the query. What are the three steps? One is the parsing and the translation, one is the optimization, one is the evaluation. Before query processing can begin, the system must translate the query into a useful form. So before beginning the processing the query, this is translated into the form, that is a relational algebra expression that is used. So for example, this is the parser and the translator that converts the query into the relational algebra expression. So before beginning with the, or before the query processing can begin, because before the processing takes place of the query, the system must translate the query into a usable form. A language such as SQL is suitable for human use but is ill suited to by the system internal representation of the query. That is, it is very suitable for the human being that is used, but it is ill suited to be the system's internal representation of the query. A more useful internal representation is one that is based on the extended relational algebra. So whenever we use the representation of the query, that is represented on the basis of the extended relational algebra. Therefore, the first action the system must take in query processing is to translate a given query into the internal form. So the first step in the query processing is to convert into the internal form so that it can be acceptable by the system. This translation process is similar to the work performed by the parser of the compiler. So it is this is the same work that will be done, that will be performed by the parser of a compiler. In generating the internal form of the query, the parser checks the syntax of the user query. So first of all, internal form will be checked, or parser is a technique, or we can say the tool that checks the syntax of the user's query, verifies that the relation names appearing in the query are names of the relation in the database, then so on. So these are the various we can say the checks that must be performed by the parser because before converting the query into the various expressions. The system constructs a parse tree representation of the query. So there will be a representation of the query in the form of a tree that is known as the parse tree representation of the query, which is given in a view that the translation phase also replaces all the uses of the view by the relational algebra expression that defines the view. So there will be a relational algebra expression that will be used. So parser converts the query into the relational algebra expressions. Most compiler text covers parsing in details. Now, given a query, there are generally a variety of methods for computing the answer. So whenever there is a query that is formed, so there are multiple options, multiple methods that will be used for computing the result, for computing the answer. For example, we have seen that in SQL, a query could be expressed in several different ways. So, for example, if I want to get the salary, so if I want to give select X that is a star from the employees, that also gives the salary, and if I individually denote the select the SQL or the select the uh, salary from the employees, that also gives the salary attribute. So for example, we have seen that in SQL a query could be designed in several different ways. Each query or each SQL query can itself be translated into a relational algebra expression in one of the several ways. So there are multiple ways in which the SQL query can be translated into the relational expression. Furthermore, the relational algebra representation of a query specifies only partially how to evaluate a query. So furthermore, this representation of a query specifies partially how to evaluate the query. There are different ways to evaluate relational algebra expression. Now this is one of the example how to evaluate. So this is select star from the instructor where salary is greater than 75,000. Now this query can be translated into the following relational algebra expression. So we can or the query processing can translate the query into the two forms, either in the projection form, either in the selection form. So this query can be translated in either of the following relational algebra expressions, that is either the selection, either the projection. So this is the pi, this is a sigma, then salary is greater than or less than 75,000, then pi salary instruction. So this is a selection, this is the projection, this is also the pi, then this is the salary, that is the instructor. So this means that query processing first of all converts, or we can say in query processing the parser technique can convert the query into the first of all the we can say the query into the relational algebra expressions. Further, we can execute each relational algebraic operation by one of the several different algorithms. For example, to implement the preceding selection, we can search every tuple in a relation or in the table, that is instructor, to find the tuples where salary is less than 75,000. So this is the method, that is every tuple in the instructor or every row in the instructor relation in the instructor table is used to find the tuples that is salary less than the 75,000. If a B plus tree that is used is available on the attribute salary, so if a B plus tree is available on the salary, so in that case we can use the index instead of to locate the tuples. Now, to specify how to evaluate a query, we not only provide the relational algebra but also to annotate with the instructions specifying how to evaluate the expression. Annotation may state the algorithm to be used. This is the for the specific program, and so on, so on, so on. Algebraic operation annotate with instructions how to evaluate is known as the evaluation primitive. So any algebraic expression that annotate with the instructions, that use with the instructions on how to evaluate the query or how to evaluate the relational algebra expressions, that is known as the evaluation primitive. Evaluation means checking or verifying the relational algebra operations that is used with the instructions, and how to evaluate with the instruction, that is known as the evaluation primitive. A sequence of primitive operations that can be used to evaluate a query, that is known as the query execution plan or query evaluation plan. So whatever the sequence that will be maintained, that will be issued to evaluate the query, that is known as the query execution plan or query evaluation plan. So that is a plan out how to execute the query, or what are the various operations that will be used to evaluate a query. Figure 12.2 shows the evaluation plan for our example, that is a example for finding the salary that is greater than the 75,000. Is the pi salary, then there is a sigma salary is less than 75,000, use index 1, there is an instructor. This is the query evaluation plan. The query evaluation engine takes a query evaluation plan, execute that plan, and return the answer to the query. So there will be a technique, there will be an engine that will be used that will plan out the, or that will take out the query evaluation plan and generates a report in simple terms. So this method, or this query execution engine, takes a query evaluation plan and executes the plan and returns the answer to the query. This gives the answer to the query itself. Now different evaluation plans for a different query can have different costs. So these are the depend on the evaluation technique, these are depend on the evaluation plan out that have a different cost. We do not expect users to write their queries in a way that suggests the most evaluation plan. Rather, it is the responsibility of the system to construct a query evaluation plan that minimizes the cost of the query evaluation. This task is known as a query optimization. So whenever we optimize the query, whenever we plan out the query to make the cost of the query evaluation, that is known as the query optimization. And query optimization is available in the next chapter, that is chapter number 13. And once the query is planned or chosen out, what happened, Larry? So the engine that is used to make the query execution plan, or that is evaluating the query execution plan, that is known as the query execution engine, that takes a query evaluation plan, executes that plan, and returns the answer to the query. That means this take the plan, executes the plan, and returns the answer to the query. The different evaluation plan, or different query evaluation plan for a given query can have different codes. So there are different plans for the different codes for the query. We do not expect users to write their queries in a way that suggests the most efficient evaluation plan, because every user have different opinion, every user have different criteria. So it is very difficult, or it is, or we do not expect from the users that they write their queries in a way that suits the most execution plan. Rather, it is a responsibility of the system to construct a query evaluation plan that minimize the cost of the query processing. So it's the responsibility of the system only to evaluate the plan out that minimize the cost of query or evaluation, and the task is known as the query optimization. So whenever we require that, or whenever we need the, or whenever we use the system to construct a query evaluation plan that goes in an optimized way. Optimized way means proper usage of the resources, that is known as the query optimization. And this is the next chapter, that is chapter number 13, that describes in detail what is a query optimization. Now next is the once the query is chosen, the query is evaluated with that plan, and the result of the query is output. The sequence of the steps already described for querying is representative. Not all the databases use the same techniques, right? And the several operations may be grouped together in the query processing, that is known as the pipeline, in which each of the operation start working on its input tuple even as they being generated by the another tuple. Now next is the measures of the query cost, that is how to measure the query cost, that is how much cost is required for proper evaluation of the queries, or proper execution of the queries, or proper optimization of the queries. That is the measure of the query cost. So there are multiple possible evaluation plans for a query, and it is important to compare the alternative in terms of the estimated cost, because when I plan something, so there are multiple plans, there are multiple, we can say, the options in my mind. So I choose one option, I choose one plan that could cost better, that could cost less, that is the estimated cost, and choose the best plan. To do so, we must estimate the cost of the individual operation. So first of all, I have to estimate the cost of the individual operation, that is what is the cost of each and every individual operations, and then combine them to get the cost of a query evaluation plan. So first of all, evaluate or estimate the cost of individual operations, that is what is the estimated cost of the individual operations, and combine them to get the cost of a query evaluation plan. So first of all, take the individual items, then plan out for the query evaluation plan. Therefore, as a study of the evaluation algorithm for each operation, we also outline how to estimate the cost of the operation, that is how to get the cost of operation. So first method is that take the individual activities, take the individual operations, and work out the cost for each and every operation, and combine that cost, or combine the cost of a query execution plan or evaluation plan. The cost of a query evaluation can be measured in terms of a number of different resources, including disk access, CPU time to execute a query, and in a distributed or parallel database system. So that is a cost that is required, that is a cost that is used for the query processing, that is a query evaluation can be measured in terms of a different resources, that is what are the different resources that is available, including the disk access, CPU time to execute a query, and in a distributed system, and the cost of communication, that is in the next chapter. So various costs, various, we can say, the different resources that is used, that will be the combined access, or the combined utility of the each and every cost of the evaluation, that is a query evaluation cost. In large database systems, the cost to access data from a disk is usually the most important cost. That is how to access the data, or how to access the record. What is the cost to access the data from the disk? That is the most important cost, since disk accesses are slow as compared to the memory operations. Moreover, CPU speeds have been improving fast and fast than the disk speed. Therefore, it is likely that the time spent in disk activity will continue to dominate the total time to execute a query. The CPU time that is required, or that is taken for a task, is harder to estimate, since it depends on the low level details of the execution cost. So whatever the CPU time that is required, that is very difficult to compare, that is very harder to estimate, because it depends on the low level details of the cost. We can use the number of block transfers from the disk and the number of disks seek to estimate the cost of a query evaluation plan. So now what are the number of block transfers from a disk, and what are the number of disk seeks? So number of block transfer, that is how many blocks are transferred, and then calculate the number, and how many number of the disk seeks to estimate the cost of a query evaluation plan. If a disk subsystem takes an average of TT seconds to transfer a block of data, and has an average block access time of TS seconds, then the operation that transfer B block and performs S seeks to would take B into TT plus S into TS seconds. So this is B is multiplied by the TT, that is a transfer time, and the S is multiplied by the TS seconds. So these are the B blocks, and the seeks, that is how many second will be required. The values of the TT and the TS must be calibrated for the disk system used, but typical values for the high-end disk today would use TS equals to 4 milliseconds and TT equals to 0.1 milliseconds, assuming a 4 kilobyte block size and a transfer rate of 40 megabytes per second. We can refine our cost estimates further by distinguish block reads from the block writes, since block writes are typically about twice as expensive as reads. So that is a block read is very expensive as compared to the read block, because it is required for executing the process, it is required for estimating the process. So we can refine our cost, we can make our cost, we can do our cost with the effective manner, so that it will be the effective judgment of the sheet, it will be effective measurement of the sheet. So when the number of block transfer from the disk and the number of disk keys to estimate the query evolution cost, that is a formula, that is B into tt plus s into ts seconds. The value of the ts and the ts must be calibrated for the disk system use, but the typical values for the high-end disk today will be ts equals to 4 millisecond and tt equals to 0.1 millisecond. This is the criteria that is used, that is a time that is required is the 4 milliseconds and the time that is required, that is the 0.1 milliseconds. Assuming a 4 kilobyte block size and a transfer rate of 40 megabytes per second, we can refine our cost estimate further by differentiating the block reads from the block writes. And whatever the cost estimate, that we do not include the cost of the writing the final result of operation back to the disk, that is required. The cost estimate that we give do not include the cost of the writing the final result of an operation, that is back to the disk. These are taken into account separately where required. So whatever the operation that will require, that will be taken in the separate way. The cost of all the algorithms that we consider depend on the size of the buffer in the main memory. So whatever the algorithm that is used, whatever the criteria that is used, that will consider depends on the size of the buffer in the main memory. In the best case, all the data can be read into the buffers and the disk does not need to be accessed again. In the worst case, we assume that the buffer can hold only a few blocks of data, approximately one block per relation. So in the best case, all the data can be read into the buffers, and in the worst case, that the buffer can hold only the few blocks of the data. When presenting cost estimates, we generally assume the worst case, that is, we assume that the buffer can hold only a few blocks of data that is required. In addition, although when we assume that data must be read from the disk initially, it is possible that a block is accessed or the block that is accessed is already present in the in-memory buffer. Also, for the simplicity, we ignore this effect, that is, as a result, the disk access cost during the execution of the plan may be less than the estimated cost. Now, what is the response time for a query evaluation plan? That is the whole clock time required to execute the plan. So response time means the whole clock time, that is a clock time that is required to execute the plan, that is the response time. Assuming no other activity is going on in the computer, there is no other activity that is required to in the computer, that would account for all these costs and could be used as a measure of the cost of the plan. So whatever the measurement that is used, whatever the plan out that is used, that will be required for the cost of the plan. Unfortunately, the response time of a plan is very hard to estimate without actually executing the plan for the following reasons. So whatever the response time of a plan is very hard to estimate. So whenever I want to estimate the response time, that is very hard to estimate because that is a clock time that is used to execute the plan. What are the various reasons while executing the plan, while getting the plan, it is very difficult to estimate the response time without actually executing the plans. What are the main reasons? The first main reason is that the response time depends on the contents of the buffer. Hello, 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 hello. Yeah, Larry, it's audible to you right now? Hello, 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 hello. Hello, 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 hello. Hello. Yeah, Larry, are you able to hear me right now? Hello. Hello. So what are the two reasons why there is a requirement of the why there is a response time, or without executing a plan there is a no response time calculation? What are the various reasons? So there are two reasons basically. The response time depends on the contents of the buffer when the query begins execution. So whatever the response time, that depends on the content of the buffer. So when we talk about the response time, that is a whole clock time to execute the plan, assuming no other activities is going on in the computer. So it depends on the contents of the buffer, contents of the data, contents of the container when the query begin execution. This information is not available when the query is optimized and is hard to account for even if it were available. So the response time that depends on the content of the buffer when the query begins execution. Now, next point says in a system with multiple disks, the response time depends on how accesses are distributed among various disks. So whenever we use a system with multiple disks, the response time that depends on how accesses are distributed among various disks. So what are the various contents, what are the various disk access that is distributed among the disks, and which is very hard to estimate without details knowledge of the data layout on the disk. So whatever the data that is layout on the disk, that is available on the disk. So there are these are the two reasons that is used while executing the already while calculating the execution time. This is a very difficult level. First is the response time depends on the content of the buffer, and in case of the multiple access, different response time is used for the different data activities. A plan must be carried out to get the better response time at the cost of the extra resource consumption. So whatever the resource consumption that is required, so there will be a better response time that is required. So as a result, instead of typing or trying to minimize the response time, optimize optimizer generally try to minimize the total resource consumption of a query plan. So instead of trying to minimize the response time, we get to minimize the resource consumption, because if there are no resources, there is no response time. So this is directly proportional to each other. If there is a high proportional, the high response time, there will be high resources. Or in simple terms, if the high resources are used, there will be a high response time. If there will be a less resources, then will be a less resource consumption of a query plan. Now, this is what we have covered in this one. Now, next is a select operation or selection operation. That is how to use the selection operation, or what are the various criteria that is used in the selection operation. In query processing, the file scan is the lowest level operator to access the files. So whenever we use the query processing, the file scan is the lowest level operator to access the data. That is, whenever we use the file scan, that is a low level operator to access the data, to get the data. File scans are search algorithm that locates and retrieve records that fulfill a selection condition. So these are the search algorithms that locate and retrieve the records that fulfill a selection condition. So these are the algorithms that helps to locate and retrieve the records and satisfy the condition, satisfy the result as a result of the query. In relational expression, a file scan allows an entire relation to be read in those cases where the relation is stored in a single dedicated file. So every relation, every file is in the entire relation that is to be read in the cases where the relation is stored in a single dedicated file. So whenever the data will be stored in a single dedicated file, that will be read out in the single dedicated files. Then in this there will be a selection that is used with the, or that is using the file scans and the indices. So what are the various conditions of operations that will be used to find the file scans and the indices? Now consider a selection operation on a relation whose tuples are stored together in one file. So select a conditional or select a selection operation, that is how to select a data on a relation whose tuples are stored together in one file. The most straightforward way of performing a selection is as follows. So whenever I want to search for the file scan and indices, what are the various operations that will be performed? The straightforward operations are as follows. First is a linear search, that is a A1. In a linear search, the system scans each file block and tests all the record to see whether they satisfy the selection condition or not. That is a linear search. That is a, in a sequence way, in a linear way, that there will be a searching that will be done in the block of the file. In case the block of the file are not stored in the sequence order, the extra seeks may be required, or we can say the extra activity may be required, but we ignore for the simplicity. Now, what are the cost estimate for the linear scan that is required for the various algorithms, that is we can say the access for the various algorithms. And the index structures are also known as the access path, that is a path that is required to locate the data and access the files. An index that is not a primary index, that is known as the secondary index. So one is a primary index, that is a clustering index that follows or that allows the records of a file to be read in an order that correspond to the physical order in a file. So wherever the physical data is required, whenever the physical files are required, that is used to access the records of the file. An index that is not a primary index, that is known as the secondary index. Search algorithm that use an index are referred as the index scans. So whatever the search algorithm that will be used as the index scans. We use the selection predicate for to guide us in the choices of the index to use in processing of the query. So whatever the selection operation that will be used, that is used to optimize the algorithm. Now search algorithm that uses the index are, these are the various search algorithm that is used in the index algorithm that is done. That is a primary index, equality on the key. That is how to get the primary index on the equality of the key. So these are the few more algorithms that will be used while using the index file, while using the index structure. So these are the few algorithms that will be used in the processing the queries. Now this is the A2, that is a primary index, equality on the key. So whenever we use the equality sign, whenever we use the equality comparison on a key attribute with the primary index, we must use the index to retrieve a single key or single record that satisfies the corresponding equality condition. So whatever the equality condition that will be used, that is the equality index will be maintained, equality operator will be used, that is based on the primary index, that is equality on the key. Now cost estimates are shown in the figure 12.3. This is a figure 12.3, that is a, we can say the base, or we can say the structure of this cost estimate for the selection operations. Next is now we will see this table. Next is the A3, that is a primary index, equality on the known key. So whatever the known key attributes, the equality will be operated on the known key attributes. And the A4 is secondary index and the equality. So both A2 and the A3 are the primary index and the equality on the key, and the A4 is the secondary index and the equality. This is the, we can say the table, we can say the form that is used, that is the cost estimate for different algorithms. So one is the A1, that is a linear search, that is a TS plus BR into TT. Then linear search, equality on the key, that is the average case is TS plus BR by 2 into TT. Then primary B plus tree index, that is equality on the key. Then primary B plus tree index, that is equality on known key. Then secondary equality on known key, or equality on the key, then equality on known key. So these are the various algorithms that is used in the query processing. Now how to select, or what are the various selection, or how to select the query that involves a, or how to select among the different comparisons. So these are the different comparisons, that is A1, A2, A3, A4, A5, A6. What are the various algorithms, or what are the various selection that will be used in the various comparisons? So consider a selection of the form, that is a sigma AVR. We can implement the selection either by using the linear search or by using the indices in one of the following ways. So what are the various algorithms that will be used? What are the various selection criteria that will be used among different comparisons? So first is A5 is the primary index and the comparison. This is also the algorithm that is used. Then the secondary index and the comparison, that is the A6. And the secondary index provides pointer to the records, but to get the actual records we have to fetch the records by using the pointer. So we use the secondary index by getting the records, by getting the actual record that we want to fetch the records by using the pointers. There will be a technique, there will be a searching technique that will be used, that is a pointer that will be used to fetch the records. Then next is the implementation of the complex selection. That is, what are the various implementation issues? What are the various, we can say the selection procedure implementation that will be used in case of the complex selection. So far we have considered only simple selection conditions of the form A, OP, B, where OP is the equality or the comparison operation. Now we consider more complex selection predicates. Now what are the various more complex selection predicates? One is the consecutive or the conjunction. That is, a conjunction selection is a selection of the form. This is the form that is used as the conjunction. Then destruction, then negation, that is a negative sign. Then the next line says we can implement a selection operation that involves either a conjunction or a disjunction of the simple conditions by using one of the following algorithm. That is this is the usage of the following algorithm that will be used to implement a selection operation. Then next is the A7, that is a conjunctive selection using one index, that is used to determine whether the access path is available for an attribute in one of the simple conditions or not. If one is one of the selection algorithm, that is A22 through A6, that can retrieve the records, that can get the records. Now A8 is conjunctive selection using composite index, that is a conjunctive selection that will be used using the opposite index, that will be available for some conjunctive selections. Then conjunctive selection by using the intersection of the identifiers, that is a A9. Then the destructive or disjunctive selection by union of the identifier, that is a A10. Now next is a 12.4, that is a sorting, that is a how to or what is the main advantage of sort the order, that is a sorting. So sorting of data plays an important role in database system for two reasons. So whenever we sort the data, whenever we can say we can purify or we can filter the data, that plays an important role in the database systems. Now what are the two reasons why this is very important, or why they play an important role in the database? First of all, the SQL queries can specify that the output is stored. So first reason is that the SQL queries can specify that the output will be stored in a proper manner. That is the first reason why this is a very important to sort the orders. Second, and equally important for query processing, several of the relation or relational operations such as joins can be implemented efficiently if the input relations are first sorted. So first of all, that the output must be sorted, or simply the SQL query that can specify that the output be sorted. Second reason is that one of the relational operations that is used, such as the joins, can be implemented efficiently if the input relations are first sorted. So it is very easy to join the two relations if it is sorted efficiently or it is first sorted. Therefore, we discuss the sorting here before discussing the join operations. So first of all, the sorting will take place, then only the join will be a beneficial. Join will take place before the sorting also, but beneficial is that whenever we do the sorting, so it is used to sort the first, then to make the join operation. So we can sort a relation by building an index on the sort key that is used, and then these are the various sort algorithm that is used. And what is the problem of sorting? That will be studied for the relation that is used in the main memory and the data files. Then the first algorithm that is used is the external sort merge algorithm. That is the algorithm that will be used that is used for the external sorting, that is the sorting of the relation that do not fit in the memory, that is known as the external sorting. And there are various sorting algorithms that is available, like quick sort, merge sort, and the heap sort. And this is the program that is used for the sorting process. And the most commonly used technique that is used for the external sorting is that the external sort merge algorithm. That is how to sort the, or what is the sorting criteria to merge the algorithm, that is the external sort merge algorithm. And this is a program that is used for the various algorithm that is defined for the various algorithm for sorting purpose. This is the query processing, this is the technique, this is the initial relation that runs sorted output, this is the create runs merge pass one. Now cost analysis of the external sort merge, that is what is the cost analysis, or how to analyze the cost in the sort merge algorithm. So we compute the disk access for the external sort merge in this way. What are the various ways in which it will be stored? Let denotes, or BR denotes the number of blocks that contains the blocks of the relation R. The first readout, or the first reads every block of the relation and writes them again, giving a total of the 2 BR block transfer. And this is we can say the algorithm method, that is the block transfer that is used for the external sorting of the relation, that is this one. Next is the join operation. So after the sorting there will be operation that is known as the join operation. So next is the join operation, that is how to do the join operation, that is the join operation. So in this section we study several algorithms for computing the join of the relations, and we analyze their respective costs. So what are the various costs, what are the various respective costs that is used in the join relation, that is used in the join operation. So we studied several algorithms that is used for computing the join of the relations, and we analyze the cost of the different join operations. We use the term equijoin to refer to a join of the form. This is the join form, that is R. This is the symbol that is used for the join. Then there will be R, then A, then S dot B S. So where A and B are the attributes, or the set of the attributes of relation R and S respectively. So there will be equijoin that joins the operation that joins the various two relations, two tables that is used. So we use the term equijoin that refers to a join of the form, that is used this one. We use as a running example the expression, this is the example. The student relation is merging or is joined with the text relation, that is using the same relation schema that is used in the chapter 2. We assume the following information about the two relations. So these are the following information that is about the two relation. That is the number of records of the student N student, that is a 5,000. Then the number of blocks of the student B student, that is 100. Number of records of the takes, that is a N takes 10,000, and the number of blocks of the takes, that is a B takes 400. So number of records that is available in a student relation, that is a 5,000. Number of blocks that is used in the student relation, that is 100. Number of record that is available in the takes relation, that is 10,000, and the number of blocks that is available in the B relation or the block relation, that is 400. Now next is the nested loop join, that is how to use the nested loop join that is used with the various categories. So figure 12.5 shows a simple algorithm that is used for the nested join, that is a one join within the another join, that is a nested loop join. It basically consists of pair of the nested for loop. Relation R is the outer relation and the relation S is known as the inner relation of the join. Since the loop for R closes or encloses the loop for the S. The algorithm that is used, that is the TR, TS, TR, TT are the tuples, and TR, TS denotes a tuple that is constructed by using the both the relations, that is R, that is a S. Like the linear file scan algorithm for selection, the nested loop join algorithm requires no indices. It can be used regardless of what the join operation is. It is used regardless of the join operation that is using. The nested loop join algorithm is expensive since it examines every pair of the tuple in the two relations. So this is a very expensive relation, very expensive algorithm, that is a nested loop join algorithm that is very expensive, that examines every pair of the tuple in the two relations. This is a block nested loop join. This is the 444. Then this is the end. Then and there will be a block nested loop join, that is a block. So if the buffer is too small to hold either the relation entirely in the memory, we can still obtain a major saving in the block accesses if we process the relation on a per block basis rather than on a per tuple basis. Figure 12.6 shows the block nested loop join, which is a variant of the nested loop join, where every block of the inner relation is paired with every block of the outer relation. That is a block nested loop relation means there will be a nested loop relation that joins the outer block with the inner block. The primary difference in cost between the block nested loop join and the basic nested loop join is that in the worst case, each block in the inner relation is S is read only once for each block in the outer relation. Now return to our example of computing start student and the takes using the block nested loop join algorithm. In the workspace, we have to read each block of takes one for each block of student. So therefore, in the workspace, a total of the 100 into 400 plus 100 into equals to 40,100 rupees. That transfer the 2 into 100, that is a 206 required. Now the performance of the nested loop and the block nested loop procedure can be further improved. So what are the various procedure, how we can improve the various procedure, how we can improve the various nested loop structures. So if the join attributes in a natural join or equal join forms a key on the inner relation, then for each outer relation tuple, the inner loop can terminate as soon as the first match is found. Then in the block nested loop algorithm, instead of using the disk block for the outer relation, we can use the biggest size that can be fit in the memory. Then we can scan the inner loop alternatively forward and the backward. Then if an index is available on the inner loop join attribute, we can replace the file scan with more efficient index lookups. The next is the index nested loop join, that is how to use the index nested loop join, that is what are the various join operation that is used in the index nested loop joins. A join method that is used is the index nested loop join that can be used with the existing indices as well as the temporary indices that is created for the sole purpose of evaluating the join. That is used for the evaluating the join, that is how to evaluate the joins. Looking up the tuples in that will satisfy the join condition will give a tuple tr in essentially a selection on the S. This is the example, that is the student is merging with the takes. The cost formula that indicates if the indices are available on both the relation R and the S, it is generally more efficient to use the one with fewer tuples as the outer relation. Next is the merge join, that is how to use the merge join or the merge join algorithm. that is also known as the sort merge join algorithm. That is sorted also, merging also, joining also. That is the sort merge join algorithm that can be used to compute natural joins and the equi join. So these are the two joins that will be used in the sort merge join algorithm, that is the equi join and the natural joins. Let R and S be the relations whose natural join is to be computed, and let R uh, we can say the intersection S denote their common attributes. Suppose that both the relations are stored on the attribute R and the S, then their join can be computed by a process much like the merge stage in the merge sort algorithm. So this is the merge sort algorithm or the merge join algorithm, that is the merging and the joining the content. So the merge join algorithm shows the merge join algorithm in the figure 12.7. This is the figure 12.7, that is the we can say the function or the we can say the program that is shows the merge join algorithm. In the algorithm, join alters refers to the attributes in the R intersection S, and the TR joins with the TS, where TR and the TS are the tuples having the same value for the join alters. That denotes the concatenation of the attributes of the tuples followed by a projecting R repeated attributes. This is the join operation that is used, that is a sorted relation for a merge relation. Then next is the cost analysis, that is the how to evaluate the cost, how to analyze the cost, that is the cost analysis. Once the relations are in sorted order, tuples with the same values on the join attributes are in the consecutive order. So once the relation are required, or once the relation are in sorted order, that is they are sorted in the order, tuples with the same value, that is whatever the tuple that is required, that will the same value on the join attributes are in the consecutive order. Thereby each tuple in the sorted order needs to be read only once. So every tuple, each tuple that is required in the sorted order needs to be read only once, and as a result each block is also read only once. Assuming that BB buffer block are allocated to each relation, the number of disk seeks required would be BR, BB, BS, BB disk seeks. Suppose the relations are not sorted and the memory size is the worst case, only 3 blocks are required. That is using the formula that is developed using the sorting algorithm, using the two relation or merging the two relations. Then the next is hybrid merge or hybrid merge join, that is also the next category of the join, that is the hybrid merge join that mixes the or that merging the sorting algorithm as well as the unsorted algorithm, that is the on the secondary indices. Then there is a hash join, that is like the merge join algorithm. The hash join algorithm can be used to implement the natural join and the equi join. So the hash join algorithm is also used, can also be used to implement the natural join and the equi join. In the hash join algorithm, a hash function h is used to partition the tuples of both the relations. That is, or that will be used to make the partition of the tuples, that is used to make the partition that is required in the tuples. The basic idea is to partition the tuples of the each of the relation into sets that have a same hash value on the join attribute. So whatever the join attribute that is required, that have a same value, that have a same data that is required in the hash join. This is the hash partitioning of the relation. This is the partition of the relation R. That is the partition of the relation S. Now these are the some basics of the partitioning. These are the some basics of the hash join algorithm that will be covered. Then there will be a recursive partitioning, that is a same partitioning will be followed in the recursive partitioning. Then next is the handling of overflow, that is how to handle the overflow, that is the handling of the overflow. So the hash table overflow occurs in the partition I of the build relation S if the hash index on Si is larger than the main memory. Hash table overflow can occur if there are many tuples in the build relation with the same values for the join attributes, or if the hash function does not have the properties of the randomness and the uniformity. In either case, some of the partitions will have more tuples than the average, whereas other have fewer. Partitioning is then said to be the skewed. So whatever the partitioning operation, whatever the skewed operation that will be used, that is used in the uniform way, that is used in the partition that will have the more tuple than the average. That partitioning is known as the skewed partitioning. We can handle a small amount of skew by increasing the number of partitions so that the expected size of each partition is somewhat less than the size of the memory. And there is a overflow resolutions that is performed during the build phase if an hash index overflow is detected. And there is overflow avoidance that performs the partitioning carefully so that overflow never occurs during the build phase. Then what is the cost of the hash function? That is on the basis, or that is based on the hash flow table, that is based on the hash flow function, that is based on the hash flow overflow. The partitioning of the two relations, that is the RS and S, calls for a complete reading of both the relations, and the subsequent operation is performed, and this operation requires 2 into BR plus BS block transfers. Then hybrid hash join, that is performs another optimization that is very useful when the memory size are relatively large. So when the memory size is large, so the hybrid hash algorithm will be required or will be used or perform more optimization, another optimization that is used with relatively large relation to fit in the memory. The partitioning phase of the hash join algorithm needs a minimum of one block of memory as a buffer of each partition that is created, and one block of memory is used as an input buffer. To reduce the impact of the seeks, a large number of blocks would be used as a buffer that can be used in the buffer algorithm. Then next is the complex joins, that is a nested loop and the block nested loop join, that is joins can be used regardless of the join operations. The other join techniques that are more efficient than the nested loop join and its variant can handle the more joins conditions, that is the complex conditions. Now, what are the other operations that will be used or that will be done on the relational operation? So what are the various other operations that is on the basis of the, that is on the base of the relation expressions? So other operations are duplicate elimination, projection, set operations, outer join, and the aggregations. So first is the duplicate elimination, that is next operation of the relational expression is that how to eliminate the duplicate, that is a duplicate elimination. So we can implement duplicate, or we can implement the duplicate elimination easily by the sorting. So whenever we sort the records, whenever I sort the records, whenever there will be a sorting algorithm that will eliminate the duplicates. Identical, that is we can say the non-redundant tuples will appear adjacent to the each other as a result of the sorting, and all but one copy can be removed. With external sort merge, duplicates are found while a run is being created can be removed before the run is returned to the disk. So with the external sort merge algorithm, duplicates found, that is while the run is being created can be removed before the run is returned to the disk, thereby reducing the number of the block transfer. So whenever there will be a disk, there will be a demand that will remove the block transfer, that will reduce the number of the block transfer, that is duplicating the eliminates, or duplicate elimination. The remaining duplicates can be eliminated during the merging, and the final sorted has no duplicate. So whenever we use the merging, so the duplicates can be removed in the merging, and the final sorted record or the final sorted data can be achieved without any duplicates. The worst case or the worst case cost estimate for duplicates elimination is the same and as the worst case estimate for sorting of the relation. So whatever the worst case sort algorithm will be used, that is the same as case of the worst case of the elimination of the duplicates. Because of the relatively high cost of duplicate elimination, SQL requires an explicit request by the user to remove the duplicates, otherwise the duplicates are retained. So it's high cost due to the relatively high cost of the duplicate elimination. SQL requires an explicit request by user to remove the duplicates, otherwise the duplicates are retained over here only. The next is the projection. So we can implement the projection easily by performing the projection on each tuple. So whatever the tuple that is required, whatever the operation that is required, we can implement the projection by performing the projection on the each tuple, which gives a relation that could have duplicate records, and then removing the duplicate records. So we can implement the projection, we can implement the projection techniques on each tuple. Duplicates can be terminated by the method that is described in section 12.6.1. If the attribute that is required in the projection, that is no duplicate, can be exist. Then next is the set operation, that is how to use the set operation, that is the union, intersection and the set difference. That is R union S, this is the first case, then R intersection S, then R difference S. Then next is the outer join, that is outer join means the join that is taken from the outer edge of the table, that is the outer join. We can implement the outer join operations by using one of the two strategies. So there are two strategies that is used to make the outer join. First one is compute the corresponding join and then add further tuples to the join result to get the outer join result. Then modify the join algorithm, that is how to modify the join algorithms. The extensions of the hash join algorithm to compute outer join is left for you to do an exercise. The next is the aggregation, that is aggregation function is required. For example, the function this one, that is the group by clause is required for the aggregation part. So this is select department name average salary, that is the department name is displayed as well as the salary that is in the average form, that is the average salary from the table instructor, and that is grouped by the department name. So we can group the department, we can group the department name into various categories, and we can use the aggregation function, we can use the aggregation method, that is a select department name average salary from instructor, that is grouped by the department name, that computes the average salary in each university department. The aggregation operation can be implemented in the same way as duplicate elimination. We use either sorting or hashing, just we did for the duplicate elimination, but based on the grouping attributes. The cost estimate for implementing the aggregate operation is the same as the cost of the duplication elimination. So whatever the cost that is required for implementing the aggregation operation, that is the same as the cost of the duplicate elimination for aggregate functions such as the minimum, max, sum, average and the count. Now how to evaluate the expressions, that is what are the various methods to evaluate the expressions. This I am not going to start right now because it's a lengthy process, lengthy step, lengthy topic that is required. So evaluation of the expressions means in simple terms, that is how to evaluate the various expression that is required in the various algorithm that is used. So this I am taking in the next class, that is in the tomorrow's class. So that's all for today's session. I will wind up this class over here only, and if there is any doubts, any suggestions, any advice, you can ask the doubts, you can give the suggestions to me. So thanks a lot everyone for listening me. Bye bye everyone. We will meet tomorrow with the topic, that is the evaluation of the expressions. Alright, so bye everyone, bye bye.